All right, welcome back. It's Friday, so once again we'll have a quiz. Again, don't panic. The quiz is simply just an old quiz that we're going to do some practice problems on. But before we get to that, we're going to have to finish up a few more data structures here. Yesterday we covered AVL trees, and today we're going to cover another balanced binary search tree called B trees. And we're going to focus on one particular kind of B tree, 2-3 trees. Right? So with a B tree, it's different from a normal tree in that the nodes can actually contain more than one key. Right? So in a B tree, nodes may contain a more than one key. Right? And what does that mean? What does that look like? Well, we'll get to an actual example here in a moment. But every node may have at most m children. Sometimes we use B instead. That's a reference to the B tree. But because you have m children, if I had 5 children, then I need to be able to disambiguate and say that, okay, well, when I'm searching for an element, it must be this child. It's not here, so it must be in this child's subtree, or that child, or that child, or that child. And so consequently, every node except the root has at least, I'm just going to cut and paste this because it's a ceiling function, m divided by 2 children. So we have a bound here. We have a minimum number of children and a maximum number of children. So somewhere in between there. The root has at least 2 children unless it is a leaf. Right? When you start out with an empty tree and you start putting stuff in, of course you're only going to have a single node tree, a seed if you want to call it that, a leaf, whatever, etc. Non-leaf nodes with k children have exactly k minus 1 keys. And this is what I was referring to before. If I have let's say that I have 4 keys, that defines 5 children. Something that is less than this key, something that is between these 2 keys, between these 2 keys, between these 2 keys, and something that is greater than all of those keys. So if I have 4 keys, then I have 1, 2, 3, 4, 5 children. Right? Or look at it another way, if I have 5 children, then I have 5 minus 1 keys. Okay? All leaves appear at the same level and are non-empty. Right? This ensures that the tree is essentially full. Now, some of the nodes may have a variable number of keys. Some of the nodes may have a variable number of children, but you are assured that it all looks like a full tree because all the leaves are at the same level. And there is nothing that is missing in the tree. There are no holes in the tree. There are some same level, excuse me, and there are some nodes with fewer keys. There are some nodes with more keys, but the actual structure of it is going to give us the assurance that it is full, and thus the depth is going to be logarithmic. We'll see that later. We'll focus on a special case, right? 2-3 trees, where m is equal to 3. And you can verify, just go back to the definitions that I just gave you. And for m equals 2, every node may have at most 2 children. Right? Every node except the root has at least 2 divided by 2, 1 child. That's kind of like a regular binary tree, but it doesn't have that same fullness requirement. For 2-3 trees, m is equal to 3. In other words, every node may have 1 or 2 keys, right? And we call these 2 nodes, which are just regular old 2, meaning that they have if they have 2 children, they only 2 or 3 keys. Oh, sorry, 1 or 2 keys. I should have been couching this in terms of not the children but the number of keys. These are called 1 nodes. I forget. And 2 nodes. That doesn't sound right, but have 1 or 2 keys, and thus 2 or 3 children. Right? We won't bother labeling those. Well, a 2 node is a node containing one key, k, with 2 children. There we go. This is a regular binary tree node, but with the connection, with the condition that both of those children have to be there. Again, this is not a regular binary search tree. It's a B tree, a 2-3 tree. So we have these additional definitions, additional structure that we're going to exploit. A 3 node is a node containing 2 keys, say K1 and K2, and 3 children. Because two nodes defines 3 splits. Everything that's less than both of them, everything that is between both of them, and everything that is greater than both of them. Right? So we have 2 nodes and 3 nodes. So how do we go about playing around with this tree? How do we do the basic operations of insert, delete, and retrieve, right? So hopefully we'll start with insertion so that we have an actual tree to play around with here. Insertion is always done in a leaf, a pre-existing leaf. If it is a 2 node, it becomes a 3 node. Right? Because before, if it was a 2 node, it only had 1 key, and we are allowed 1 or 2 keys. So if it only has 1 key, then it's large enough to accommodate that second key, and it just magically turns into a 3 node. Right? I say magically, but in an actual implementation, you would have a class representing a node, and within that class, you would have some sort of a list data structure, like an array or a linked list or something like that. If it is a 3 node, you promote the middle key or middle key element up, potentially overflowing the parent and potentially overflowing the grandparent, and you just have to keep going all the way up until you potentially have to create a brand new root node. Okay, so what does this look like? Let's go ahead and insert. Let me jump over here to the tablet, and let's do an example. Right. So we're going to insert the same numbers that we were playing around with yesterday. Just to remind ourselves, that's 8, 4, 7, 3, 2, 5, 1, 10, and 6. Okay? All right, so we start out with a normal empty tree. Okay, there's nothing in there. When I insert 8, that becomes a new 2 node, right? And it's pretty straightforward. That's exactly how you would do it with a regular binary search tree. Now let's insert 4. We start at the root, and we insert, and we see immediately that this is a leaf at the same time. There's nothing down here. So we're going to insert it, and this 2 node then becomes a 3 node. And we have ordered here 4 and 8. And you can see how this could potentially have 3 children now. Everything that is less than 4, everything that is between 4 and 8, and everything that is greater than 8. We don't have any children yet because we haven't inserted them yet. Okay, so there's the first 2. Now we insert 7. 7. Now the way that I'm going to depict this is that temporarily this will become a larger node, a 4 node if you want to call it that. With 4, 7, 8. Note that inside the node here, I am maintaining the order 4, 8. I didn't say that it was 8, 4. So internally, the node has to also keep everything in order. Right? Remember, we are on Piazza. If you have any questions, go ahead and post there. Otherwise, I am taking a look at the streaming. If you have any comments on YouTube, okay. Anyway, back to this. It temporarily overflows. Now we can't. This is not a 2-3 tree, and so one of these guys has to be kicked out. And what we end up doing is we end up kicking out the middle element here, and promoting it up. Well, at this point there is nothing up here. So if we promote into nothingness, that means that we are creating a brand new root node, and it ends up becoming 7, and its 2 children are now 4 and 8. which looks exactly like a regular old binary search tree. But remember that it's a 2-3 tree, and this is why it's balanced. Now everything is all the levels are filled. Right? We don't have any holes in this. Some key, each of these keys is only a 2 node, or each of these nodes is only a 2 node. So we now can accommodate more elements. Right? So that takes care of 7. How do we insert 3? Again, we start at the top here and see that 3 is less than 7. We don't insert here. Yes, there's room to insert here, but we always insert as a leaf because that promotion, that overflow, needs to go up. So we could, so we're not going to insert at 7. Instead, we're going to go down to its left child because 3 is less than it. And there is no left child here. This is a leaf, so we end up inserting it there. And this becomes 3, 4. There we go. That 2 node becomes a 3 node. Now what happens when we insert 2? Same process here. We don't insert it here because that's not a leaf. We go down to this leaf and see that, oh, it can accommodate, this is the leaf, so we're going to temporarily try to put it in that thing, that node, temporarily overflowing it basically. So 7, 2, 3, 4. But we need to correct for this now. It's too big, right? We can't have 3 keys in this because it's a 2-3 tree. If it were a 3-4 tree, then yeah, we're talking about a different scenario. But we're gonna have to kick somebody out. The guy that we can kick out is always going to be the middle guy. Right? We're going to promote that up to the parent there, and when we do that, we get 3, 7, and 2, 4. Temporarily. Right? This is done in stages here. But you see what the problem is here. By promoting this up, by promoting 3 up, this 2 node has now become a 3 node. 3 nodes have 2 keys and they have to have 3 children, which is fine. What we can do is we can split this node up into 2, and besides, the binary search tree property is already violated, right? Everything over here less than 3, 2, 4, 4 is not less than 3. That's fine because when we correct for this and split it out, we get 3, 7, still in the root, and 2 and 4 get split out into their own nodes, 8. Right. Now we've got a 2 node and all 3 of the children are present. Okay? 2 is done. What about 5? So 5 comes into a 2 node here, or sorry, a 3 node here, and we would make several comparisons, right? 5 is not less than 3. 5 is greater than 3, but it's less than 7. So we know that if it exists, it should go down here. So we go down here to this node and see that it's a 2 node, and so it can accommodate, and it's a leaf, so it can accommodate that new element. 3, 7 is still up there. 4, and now 5 are part of that node. There. So 5 is taken care of. Likewise, when you bring in 1, it's going to go to the left and see that you can accommodate that. And so I'm going to go ahead and erase this and just so I don't have to rewrite everything. And now we have 1 and 2 was in there before. There we go. We bring in 10. Same story here. It comes down to the right, and that 2 node becomes a 3 node with 8 and 10. At this point, we have a completely full 2-3 tree. There is nowhere else to put that last element 6. So necessarily what's going to happen is it's going to be restructured. So let's go ahead and come down here, and 6 goes in the middle. So temporarily 6 will be added to this. We take 5 and we promote it up. Let me draw that in one step here. 3, 5, 7. Right, that's too big, so I'll put an asterisk there. 1, 2, and then 4, and what was it, 6? Yep, 6. And then over here was 8 and 10. And again, we came down here and we inserted 6 in here. Okay. Well, that's not a 2-3 tree because we've got a node here that has 3 keys and 3 children here. So what we need to do is we need to take 5 and promote it back up. Again, it could by promoting something up, you could cause overflow in the parent, like we did over here, right? Over here there was no parent, so what we ended up doing was we promoted up again, and we get a brand new root node: 5, 3, and 7. But now remember, down here we've got 3 children. If these two split out into 2 nodes, to a 2 node and a 2 node, then we also have to split these children. This one will become the left child of 3, 1 and 2, and then where we actually inserted something, that's where it gets split up. This 3 node is going to get cut up and made into 2 nodes, 4 and 6, and then finally 8 and 10 are still over here. There we go. All right. And again, it ensures this fullness property so that that everything is at the same level. It could be that some of these things have 2 keys, some of these things have only 1 key. But the fullness property ensures that the depth is always going to be logarithmic. Let me prove that claim. Sorry, it's all from yesterday in office hours. There we go. All right. So let's think about this. What is the maximum number of keys in a 2-3 tree of depth D? Right. Well, if you're trying to maximize the number of keys in a 2-3 tree, that means that every node is a 3 node, right? And so has 2 keys, right? So how many nodes are there? This goes back to computer science 2, where, all right, so we've got this node here, and it's of depth, well, here, they're 3 nodes, so there's this node here, and then there are 3 children, right? Each one of those will necessarily have 3 children. Right? Each one of those will necessarily have 3 children. And it's going to be of depth D. This is at depth 0, this is at depth 1, this is at depth 2. So let's try to figure out a pattern here. At depth 0, the number of nodes, because of the fullness, because it's basically full, is going to be 1. At depth 1, we've got 3. At depth 2, we've got, hopefully you count them up, 9, ... At depth D, we have that there are going to be this pattern here of 3 to the D, right? So what is the total? What is the summation of I running from 0 up to D of 3 to the I? Well, you can stick that in Wolfram Alpha if you want to. Otherwise, I believe that it's going to end up being 1/2. Don't quote me on that. Darn it. It's a geometric series, and I think that that there's a generalization of any x to the I for running from 0 up to a D is going to end up being something like 3D plus 1 all over 2, I believe. Right? Let me just, don't quote me on that. Okay, -1, of course, up top. There we go. All right, good. So that's the number of nodes. This is the number of nodes there are. We said that every node has 2 keys. So therefore, what is the total number of keys? Well, when I multiply the number of keys by the total number of nodes, that 2 on the bottom and the denominator goes away, and we have 3 to the D plus 1 minus 1. Right? That's an upper bound. on the number of keys that a 2-3 tree of depth D has. What about a lower bound? What are the minimum number of keys in a 2-3 tree of depth D? Right? Well, this is just a regular old binary search tree, right? Every node has one key. And how many nodes are there? Same analysis that we just did, and even the same formula. If you look up the generalized formula, but just to show you here, depth 0. At depth 0, there's going to be one node. At depth, because it has necessarily has two children. At depth 1, it has two nodes. Each one of those has two children, and so at depth 2, it has four nodes. ... At depth D, they're going to be 2 to the D nodes. Right? And so when we sum that up, we get summation of I running from 0 up to D of 2 to the D. And here it's going to be 2 to the D plus 1 minus 1. Right? And since each one only has one key, we multiply that by 1, and that's also the number of keys. Right? So n being the number of keys is bounded below by 2 to the D plus 1 minus 1 and 3 to the D plus 1 minus 1, right? Or thereabouts, right? So we can go ahead and take off one on each side. What I want to do is I want to get this in terms of D. If I had a tree of what is the depth, right? If I had a tree with n, a 2-3 tree with n keys, I want assurance that its depth is going to be logarithmic with respect to n. So let's go ahead and ignore those lower order terms first of all, and we get 2d plus 1 less than or equal to n less than or equal to 3 to the d plus 1. Now you can solve for either one by taking the logarithm, right? Log base 2 over here of this and log base 3 of this over here will get you that d plus 1 and then the log goes away is less than or equal, and of course you'll have to take log of n. Let's just do this first one here, this first inequality. D is less than or equal to d plus 1 is less than or equal to log base 2 of n, right? And what about this one right here? Oh, I get log base n, log base 3 of n is less than or equal to d plus 1, right? So d plus 1 is bounded. It's bounded below by log base 3 of n, right? And it's bounded above by log base 2 of n, right? So plus 1, you can go ahead and ignore that, right? The depth is going to be order n. In fact, it's going to be theta log n, right? Because it's bounded above by a logarithm and it's bounded below by a logarithm, and all logs are the same to within a constant. If you want to switch this one out to a log base 2, that's fine. There's just this this constant sitting out front, and you can convert that to a different base. So we've achieved the goal here of ensuring that the depth is always going to be logarithmic with respect to a B tree, right? Okay. And there's this other online kind of visualization here. Again, we can confirm those numbers that I was using. We can see it animate, right? Let's go ahead and insert 8. Let's go ahead and insert 4. Right? And you see that it becomes 4, 8. Right? It's kind of hard to see here, but you can zoom in. You can use you can just do a Google search for this. There are a couple dozen of these visualization tools out there. 7 comes in and necessarily overflowing it, creating a new root node, and the 3 node becomes 2 nodes with a new 2 node at the top. 3, that'll get inserted as a left in the left child, making the 2 node into a 3 node, and you're good. 2, that's where that left child is going to get overflown, and 3 gets promoted back up, creating a 3 node with 3 children for it. Right? And then you can go on like that as well. Okay. All right. Well, how do you end up? Let's complete it, I guess. Hopefully you understand how you can also search this stuff. Let me go ahead and create it. 5 gets inserted there. 1 gets inserted in the left child. 10 gets inserted in the right child. And then the last straw here, since it's all full already, right? And you'll note here that this is of depth 1. How many are there? How many keys are there? If you plug that into the formula that we had before, there are going to be 1, 2, 3, 4, 5, 6, 7, 8 keys. That's 3 to the 1 plus 1, so 9. And then there was a -1 factor there. That gives you 8. Right? So let's insert this last one here, which will overflow the middle one, promoting 5 back up. And then that overflows that, and ultimately it creates these a new root node there. Right? How do we go about searching this? Hopefully it's pretty straightforward here, right? We had to find which leaf to insert it in to begin with. So if you're going to search for something, say 6, just like a regular old binary search tree, you start at the root and you go traverse left or right, or in the middle if it's a 3 node, to find what you're looking for. How do you delete things? That's where it gets complicated. In the book, I've got, or in the lecture notes, I've got about a couple dozen diagrams of different situations. Basically, if you delete something in a leaf and it's a 3 node, that's really easy. It just becomes a 2 node. If it was a 2 node, you can't just have this hole there. You can't just have this leaf. You need to borrow a key from somebody else. And so what you have to end up doing is you look to your siblings. Can you shift things around in order to get another key to fill that hole? Or if you can't borrow one of your siblings, then you go to your grandparents. And ultimately, the worst case is when you have nothing left to borrow and you ultimately collapse the tree down one level. Right? It can get quite complicated. There are a lot of situations, a lot of different conditions. And that's why I've got like a dozen or so diagrams showing you how it would work. All right, but we're not going to cover that level of detail here. No questions so far. So we have plenty of time here. But before we move on to the next data structure, let's go ahead and think about Friday here. It is a quiz day. Again, under normal, I guess if it's sort of a regular course, I would, like in-person course, I would be administering these quizzes. Instead, what we're going to do is we're going to use these quizzes as review. All right. So here's a quiz from 2 years ago. The Tombcook algorithm, which is an actual algorithm, is a divide and conquer strategy for multiplying two n-digit integers. A particular variation on this algorithm splits the two integers into 3 parts, each 1/3 the size of the original. The recursion, however, requires 5 recursive multiplications. Set up a recurrence for this algorithm and provide an asymptotic characterization for it. Is it better or is it worse than Karatsuba multiplication? So this is all just asking you to set up a recurrence and use the master theorem to provide an asymptotic characterization of it. Remember that with Karatsuba multiplication, there was no non-recursive cost. We split these 2 big numbers up into 4 smaller numbers, and then we did 3 multiplications. So that required 3 recursive calls. So let's go ahead and go over to our tablet here. With the Tombcook algorithm, that requires, like it said, it splits 2 integers. Oops. 2 integers into 3 parts, each 1/3 the size. But it makes 5 recursive multiplications. So if I let m sub n be the number of multiplications by, and this is Tombcook, on two integers of n digits, then the recurrence would end up being I have 5 recursive calls on an input that is 1/3 the original size. So that's something you might not have seen before. It's always been 1/2, right? This one, or except for ternary search, if you've seen that. And then you can show that ternary search is no better than binary search asymptotically. But 5 multiplications, and then again, no recursive cost, so we don't even bother writing that. Right? So applying the master theorem here, A is equal to 5, B is equal to 3, and then D, the non-recursive cost there, that's bounded by by a polynomial of degree 0. Right? And so what is the relationship between A and B to the D? Well, it's greater. So I believe that that is case 3 of the master theorem. We can pull that in. Let's see, master theorem. There we go. Just to remind ourselves what it looks like. Right. Indeed, that is case 3 of the master theorem right there. And so what we have is that m sub n is order, or theta, n to the log base b, in this case that's 3, so log base 3 of a. Now I have no idea what that is, and you can pull up Wolfram Alpha if you really want to. I really don't memorize these things, so I didn't memorize Karatsuba. But you can go back to your notes and find out what was the exponent. I believe it is better. It is faster than Karatsuba, asymptotically. This exponent right here is probably going to be less than whatever Karatsuba was, and so you would answer yes. That's just plugging and chugging into a calculator or Wolfram Alpha. That's just not memorization. That's looking up what the original algorithm is. That's why it's always open book, open note with me, right? I don't care that you memorize that, because I don't. You just go back to your resources to find out what was it, right? What was that number, right? And then, of course, it requires you to think about how can I apply the master theorem? How can I set up a recurrence relation? How can I apply the master theorem? And a basic knowledge that polynomials have different orders of growth, and so one of them is definitely better than the other. Right? All right, transition back over here. The second question here is consider the binary search tree in Figure 1. For each node, indicate the balance factor. So I've already cut and pasted a picture of this. So let me go ahead and add it, and then there it is. And then I'll transition back over here. I'm going to do one better. Let's go ahead and list out the height and the balance factor for each one of these. So the node, the height, and the balance factor. Right. In fact, I mean, we can just do a subset of these or something. 5. I'll start at the bottom because that's the easiest. 5 has no children, so it is already a leaf. The height of any leaf is, by definition, 0. The height of an empty tree is going to be -1, remember. So what's the balance factor? Since it has no children, right? It has a -1, -1. You subtract these, and you get 0. And so it has a balance factor of 0. And I can jump ahead here and look at any leaf is going to have the same value. So 9, 15, 20, 25, 27, 31, 41, 50, 57, and 75. 57 is going to be 0 and 0. 41 is 0 and 0. 27 is also 0 and 0. What about the rest of them? 9. Its height is, again, the height is the longest path to any of its descendant leaves. There are no leaves over here in the right subtree. There is a leaf in its left subtree, and the path that it took to get there is 1, so its height on 9 is 1. What about its balance factor? The height of its left subtree is 0. The height of its right subtree is -1. The difference between those is going to be a +1. Right? And that's good. That gives you the intuition here is if it's positive, then it is skewed to the left. If it's negative, it's going to be skewed to the right. What about 15? Well, it's 1 up, so the height is going to be 2 here. Likewise, I can jump ahead. What's the height of 20? 3. What's the height of 25? 4. Right? All I'm doing is looking at this path that's going back up to 25. And therefore, since 25 is the root, the height of the entire tree is 4. Okay? But it also, it's very, very skewed to the left here. So you can imagine what the balance factor is going to be. It's going to end up being 2, 4, and then, I don't know for this because there's actually a right child over here. But let's go ahead and go through the exercise here. The balance factor of 15. Its left subtree has a height of 1. Its right subtree has a height of -1. And so when I take the difference between those two, I get a 2. Right? Same thing with 20. The left subtree has a height of 2 minus the height of the right subtree is -1 because it's empty. And so I end up with 3. What about 25? If I look ahead here, the height of this tree, 31 is going to have a height of 1, 2, 3, or another perspective, 1, 2, 3. It's not with respect to its nearest leaf. It's with respect to its lowest leaf. Right? So 1, 2, 3 is the height of 31. Right? We'll worry about its balance factor later here. And therefore, the height of the balance factor of 25, again, the height of its left subtree is 3. The height of its right subtree is 3. And when I take those, the difference between those, they end up canceling each other out. So from the perspective of 25, this tree is balanced. But from the perspective of 15 and 20, it's unbalanced. And this is certainly not an AVL tree. This is certainly not a configuration that you would ever get from doing an AVL tree. Okay. What about 31? Well, let's start. Let's start at 50. It's completely balanced, so 0, and its height is going to be 1. The only remaining one is 75. 75 has a height of 1, 2, and there's nothing over here to compete with that number, so 2 on its height. The balance factor of 75 is going to be 1 because its left subtree has a height of 1 minus, and then its right subtree has a height of -1, so it ends up being unbalanced as well, 2. Finally, what about 31? What's the balance factor on 31? Well, it's going to be 0 because its left subtree has a height of 0. And its right subtree, 75, has a height of 2. The difference there is negative, right? And that's -2. It's skewed to the right, unacceptably so for an AVL tree, but again, this is not an AVL tree. All right? Going back to the quiz over here. Consider inserting keys into an initially empty AVL tree in the following order: 30, 20, 10, 40, and 50. Show the resulting tree and any rotations. And then jumping ahead here, do the same thing if it's a 2-3 tree with the same keys. Okay? So 30, 20, 10, 40, 50. All right? Just write that down. 30, 20, 10, 40, and 50. Okay? So an AVL tree. The first couple of examples are not, the first couple of inserts are nothing special. 30, there's step 1. 20 will get inserted as a left child of 30. Right? Now 10. 30, 20, and 10. And you can see immediately that this is going to be unbalanced to the left, and so you want to do a right rotation. But just to get more practice here, what are the balance factors? 0. 0 on this one, it's 0 minus -1, so that'll end up being +1. And on this one, it'll end up being 1 minus -1 and giving me +2, skewed to the left. And so I end up doing a right rotation and restoring its balance to 20, 30, 10. This is, in fact, the canonical right rotation that we always show introducing this. So what about 40 and 50? Well, 20, 10, 30, 40 gets inserted as the right child of 30. No rotations there. If you did end up rotating this around, you would necessarily put one of these keys down lower, and that's no better than what you started out with. Okay. What are let's get some practice here. What are the balance factors though? 0, 0. The balance factor of 30 is going to be -1 minus 0, because there's no left subtree. There is a subtree on the right, but its depth or its height is 0. So it's going to be -1. It's skewed to the right. What about 20? It's going to be 0 minus 1, and so it's also -1, but that's acceptable for an AVL tree. That's why we ended up with no rotations. Okay. When we insert 50, we end up with the final initial, penultimate maybe, configuration that looks like this. Now what are the balance factors? 0, -1, because it's -1, -1 minus 0, so -1, and 3, it's skewed to the right, so -2 here. Now, the balance factor at 20 has been disturbed, but we don't go all the way up until we find the shallowest unbalanced node and rotate there. We stop at the first imbalance and then rebalance it. And that'll actually end up fixing the balance factor at 20, and we don't even have to change it, at least in this case. So we end up doing a left rotation, giving us the final configuration here of 20, 10, 40 comes up to be the new right child of 20, 30 comes down, and 50 comes over here. And you can see very easily that that is indeed a binary search tree. All right. What are the balance factors? Just to make sure here, 0, 0, 0, because it's perfectly balanced there. 0 here. What about the balance factor at 20? Remember, before it was -1. Did it change? Well, the balance, the height of its left subtree is 0, minus the height of its right subtree, 1, and so it becomes -1. It didn't change, at least in this case. Right? In fact, in all inserts, it will only affect local information. For deletes, you could have a propagating effect all the way up to the root node. All right. Copy that. There we go. Now what about a 2-3 tree? All right. So almost the same story here. At least for the first iteration. 30 gets inserted. Then 20 gets inserted. And the 2 node becomes a 3 node. No changes yet because it can accommodate that. Then 10 gets inserted. 10, 20, and 30. And unfortunately, that's too full. So we end up with 20 being promoted up into a new root. 10 down over here, and 30 down over here. Next thing to insert is 40. So 40 is greater than 20. 40 gets inserted over here. And we have 20, 30, and 40. Remember, it always gets inserted as a leaf. There we go. What about 50? 50 will get inserted as a leaf on the right child, so 20. 10 is still over here. And 30, 40, 50. But It's now too full. Somebody's got to be kicked out. 40 gets promoted up to 20. So it looks like this. 40 and 20 are at the root. You still have 10 hanging off over here. And then you have 30 and 40, or 30 and 50, excuse me, temporarily. But since that promotion of 40 has caused this to become a 3 node, it now needs 3 children. So we end up splitting this into 2. 40 it was 30, sorry, and 50. And there's the final configuration of your 2-3 tree. Okay. No questions on that. Again, these quizzes are very, very similar to what your midterm, in spirit, to what your midterm is going to be like. Yes, of course, you could have used that online tool to do this, to verify your answer. It might not be so easy if we start with like an intermediate tree. So you do need to know how these rotations work, how the balance factor works, and things like that. Okay? All right. So our next data structure, which we'll start today here, is based on hashing. Whoops. Not rehashing, but just hashing. All right. So you've heard us frequently tell you use a map, and implementation of that is a hash map. I've made posts on Piazza telling you why there's not like a built-in binary search in Python. Instead, you'd have to bring something in because there are much better data structures to use, and they're hash-based data structures. So again, balanced. When we start out with list-based data structures, some things are really efficient, like adding a node to the head of a linked list. Some things are really efficient, like lookups in an array, if it's an array-based list. But we found out you find quickly that other operations for each of those, there's a trade-off, and inserting something arbitrarily in the middle of an array-based list, that ends up being a linear operation. Searching through a linked list because you don't have random access, that ends up being a linear operation. Even balance, and so that's when you are introduced to trees and heaps, and those offer the promise of efficient insert, delete, and retrieval methods. But of course, you need balanced binary search trees to guarantee all operations are order log n. So at least at the beginning, you think, okay, well, that seems like that's the best you can do. But what we want is, you can do better. You can do constant time, right? So hash-based data structures, that is sets, hash tables, maps, right, etc., offer order 1 amortized operations. Right. And we'll see what that means here momentarily. Okay. So you might ask yourself immediately, why do we even bother with lists? Why do we even bother with trees? If hashing offers order 1 amortized operations, why don't we just start with those and go with those, and those are the only data structures that we'll use? It's because there are some drawbacks to it, and there are some limitations. For example, if you want ordering, right, then you're going to be using a combination of hashing and something else, or you're going to be keeping track of additional information. If you want arbitrary operations, remove something, then its performance can degrade. That's why we say that we give it with a caveat that it's amortized operations. We'll understand what that means later here. But here are the basic ideas that we'll start out with. Right? Elements are stored in a contiguous, fixed-sized array. Right? That is, we have easy, that is free, and I'm putting that in quotes there because nothing's free, random access to elements based on their index. Right? So just like a regular old array, if you want the fifth element, the element at index 4, here you go. It's just a memory offset. It might be a cache miss or whatever, and it has to load it. But here you go. It's pretty much a constant time operation, right? So we're off to a good foot here, right? We've already got constant time. The actual index / location of each element, I'll call them x. Right? So we've got this x here that we're trying to store in the hash table or the hash-based data structure. Is determined by using a hash function. Right? And usually we use h of x to denote this. Right? The object here, so you might immediately say, well, okay, what is ultimately a hash function is going to be an integer. Because we want our indices are integers. You can't have the element at index 3.5. You can't and they're probably going to be non-negative. You can't have an element at -4, right? It just doesn't. I mean, you can think of it in terms of that, where it's a memory offset, but you're starting at the end or something. But that's not usually how a computer works. As long as the hash function is easy to compute, then the index is easy to compute and efficient. All I know is I need to know where this x element is, run it through the hash function, and it tells you it's at index 42. I jump to that location and I found x. Now x, here a couple more caveats here, right? Generally, you use a key instead of the actual object. That's where maps come in. Otherwise, you could automatically say, well, if I have x, why do I need to put it already? Why do I need to put it through a hash function to find out where it's located? Just to find it. I've already got it right here, right? Well, that's not usually how it works. You have a partial key or a surrogate key or something like that that partially represents the object that you're trying to store, or you're using an entirely different key, like in a map. You use strings to map to integers, or you use strings to map to student objects or something like that. So in other words, it is sufficient to consider integers as both input and output to a hash function. Right? Well, what about objects? What if you did want to store objects as your key values, right? Objects generally can, the object state, unobjects state, there we go, can generally be used to provide a non-unique integer representation of the object called a hash code. Now you might have seen this from Java, or you might have seen this from a couple of other languages. Java had this built in from the beginning. It made sure that every object has this hash code function, a hash code method that based on the state of the object or some other criteria, gives you an integer representation of that object. Now, by default, that hash code value is simply just some integer representation of the Java virtual machine memory address. Other languages could be very similar. Wherever it's stored, that's who I am. That's my identity or something. Generally, you want to override that condition to be based on the state of the actual object. If you've got a student object with a name, first name, last name, NUID, and GPA, you would want your hash code to be based on all four of those things. Built-in elements such as integers, strings, doubles, they already have hash codes that you can bring to bear. Right? That generally is part of the language. So my caveats here are you don't have to think in limited terms of just integers, but it's sufficient to do so. Okay. All right, so generally a hash code, or a hash function, excuse me, will map the following. And here I'm just going to cut and paste these. If you've not seen this before, H is the function. Z in this Blackboard bold font here, that is all integers. It's mapping every integer, an infinite number of integers, down to a set Z mod M. Right? What is that? Well, Z mod M. Let me define that for you. Is equal to the set 0, 1, 2, ... and m minus 1. Right? It's the remainders. That if I take an integer and I divide it by m, mod m, and I take the remainder of that, then that's what it maps to. And why do you want to do this? It's because that allows the hash function to map to indices 0 through m minus 1. In other words, to an array of size m. Right? That's why we're doing it like this. Now, there are other more fancy hash codes. There are lots of other applications of hash codes, or hash functions, excuse me. Cryptographic hash functions to store passwords securely. In this particular case, though, we're using them for storage of data into a data structure, into a hash-based data structure. So since we're choosing to use an array to do that, we just simply need Z mod M. Right? You can get a lot more complicated than that. In fact, let's take an aside here. Why are they called hash functions? Right? Let's go ahead and visualize that type of function there. So here's Z. Right? That's the set of all integers. That's an infinitely sized set. It's getting mapped down to this set of size m, right? Where you've got 0, 1, 2, ... down to m minus 1 at the bottom here, right? So some of these things necessarily will map to the same subset over here. I could have these two elements. When I divide both of them by, say, m is 17. When I divide 34 and 68 by 17, I have a remainder of 0. They would get mapped to the same bucket over here. Okay. If I have, say, 25 mod m, that's going to be mapped to 8 somewhere over here, right? So this is where hash functions get their name. By mapping this very large set, in fact, an infinitely sized set, into a small set, I've basically partitioned up the set of all integers. I've hashed them up. That's what hashing means. Hash browns, you cut things up, you chop things up. So I've chopped up all of the integers into a set, into 17 pieces, right? So that they're digestible. You can't eat an infinite number of things, but if I chop them up, and here's only 17 things, now you can go ahead and eat your hash browns. But that's the idea. That's why it's called hashing. That everything has its own bucket after you compute the hash function value. Right? Okay. Well, necessarily that means so let's go ahead and take an example demo. Right? And I don't have any numbers, so let's just go ahead and make up some numbers here. All right. I don't want it that big, so let's go ahead and say, suppose that m is equal to 7. So I'm going to have an array here of size 7. That's indices 0, 1, 2, 3, 4, 5, and 6. There we go. And what about my hash function? Hash of x, it doesn't really matter. You can have a linear hash function, you can have a quadratic hash function, whatever, as long as you're modding out by 7 so that when you get the remainder, it's one of these 6 values right here. So what I'm going to do is I'm just going to pick another prime here, 3x plus 11, and then mod m, in this case 7. Right? So let's go ahead and just make up some random numbers here. 28, 32, 17, 41, 101, 8, 3. Okay, and I'm going to add a 4 over here to start out with. Let's insert these in sequence. So what is the hash value of 4? That's 3 times 4, 12, plus 11. Right? That's 33. When I mod out by 7 here, mod 7, that's going to give me a remainder of 5. So 4 is going to map to 5. Right? Great. 28. The hash value of 28 is going to be 3 times 28 plus 11 mod 7. Right? And at this point, I am going to have to appeal to Wolfram Alpha. Just to make sure that I am getting all of my numbers correct here. You're on a 10-second delay, so if you want to shout them out, great. Oops. Pretty sure it's 4, but I want to make absolutely sure. So 3 times 28 plus 11 mod 7. Yep, it's 4. So 28 gets mapped to 4. Doing good so far. 32. H of 32 is equal to 3 times 32 plus 11. So that's going to be 96 and 107 mod 7. That's going to be 2. Doing good. All right. There we go. So 32 gets mapped to 2 there. H sub 17 is going to be 3 times 17 times 17 plus 11 mod 7. And that's going to end up being 6. Good. So 17. Next one is going to be 44. H sub 44 is equal to, or sorry, that's 41. There's nothing special about these numbers. I could have changed it to 44. But 3 times 41 plus 11 mod 7. So 41 is going to be 1. And so 41 goes up to 1. To index 1. H sub 101. Oops. Is 3 times 101 plus 11 mod 7 is equal to 6. Good. Couldn't have picked better numbers here. What happened? 101 wants to go to 6, but somebody's already living there, right? Throw up our hands. Up, we're full. You can't go find somewhere else to live. Find somewhere else to be. This is called a collision, right? And it was actually very, very predictable that we were going to have this because of the nature of the hash function. You're trying to fit an infinite. In this case, you're trying to fit an infinite number of numbers into only 17 slots. Necessarily, by the pigeonhole principle, one of these slots is going to have more than one element. And for this particular example, I made it through 6 numbers, excuse me, before we had our first collision. Right? These two have collided. Just like 34 and 68 over here, they collided by being mapped to the same element. So what do? Do we throw up our arms and quit? Well, no, what we need is a collision resolution algorithm. What are we going to do about this? Well, one thing that you can do is, okay, well, you can't go here. So is there somewhere else that you can go? Right. Well, I'm going to go to the next cell. but there is no next cell. So I wrap around to the start of the array, and I find out that, hey, there is a room for me now, right? 101. There we go. Okay, that sounds like an okay solution for now. Let's go ahead and continue here. H sub 8 is equal to 3 times 8 plus 11. Mod 7 is equal to 101. Oh, sorry. I haven't computed it yet. What is it? 24 and then 35. So it'll end up being 0. And so 8 wants to go to 0, but we just accommodated 101 there. Okay, well, let's take the same strategy. You can't go there, so go to the next cell. Well, you can't go there either, right? Next cell, you can't go there either. Musical chairs, right? So everybody's taking a chair. Is there still a chair? Nope, go to the next one, go to the next one. Okay, there, finally, I can put 8 in there. Now we can go ahead and try to hash 3, but you can see immediately that the hash table, the array, is already full. This collision resolution is no longer sufficient, right? Not only that, but it comes with some drawbacks here. What if I wanted to search for 8, right? I would end up computing its hash value and seeing 0. And when I jump to 0, I say, oh, 101? That's not what I'm looking for. How do I know if it's in there or not? I have to go to the next cell. That's not it. That's not it. That's not it. ... until I get to either an empty cell, in which case I know that if 8 had been inserted, then it would have been inserted in this empty cell here. And so I can stop and say unsuccessful search. It's not in the hash table. Or I end up going all the way around the entire table and finding it at the last point because it's full, right? So full hash tables have basically degrade into regular old linear search, regular old arrays. So the hashing doesn't buy us anything if it's very, very full. This is called linear probing. That you go to the next one, you go to the next one, you go to the next one until you find something there. And there are lots of little other, ifs, ands, and buts there that you have to work out the details for. For example, what if I ultimately deleted 101 from the hash table? Now when I come in and want to search for 8, and it is in there, if I come in here and say, oh, well, it's not there, so it must not have ever been inserted, that's not true. I also need to keep track of the fact that this cell was actually used at one point, right? So these are usually called dirty bits, right? A dirty bit, right? Where you can set it that once this cell has been filled, you mark it. Even if something ends up getting deleted after that cell, you still have to keep track that it was once used. And eventually, everything gets used. So even if there's nothing in the table, you still have this table that, well, it's been completely used and you don't know where anything is anymore. It worked nice at the beginning when the table wasn't very full, right? So what do we do now? The solution is to create this brand new table that's even larger to accommodate all these elements. And in fact, you do that periodically. These are the details that we'll go over on Monday. But basically, if it gets too full, say 75% full, you take everything out of the table, create a brand new table that's twice as big, say, and then you rehash everything, maybe even with a new hash function. In fact, you have to have a new hash function because your modulus has changed, because your size of your table has changed. So that's ultimately what happened. There are a couple of other collision resolution strategies that we'll also talk about. Again, instead of using linear probing, you can probe with a secondary hash function. Instead of using linear probing, you can hang things off and accommodate it with an entire linked list. That's called chaining, right? And so you don't linearly probe; you just make room for it by adding it to the end of the chain down here. It doesn't have to be a linked list. It could be a tree. It could be a balanced binary search tree, like an AVL tree. It could be any data structure associated with this cell. Again, the problem there is if it gets too full, then it devolves into no better than an AVL tree. In fact, in this case, you would have 7 AVL trees instead of 1 AVL tree. That cuts down in practice. That cuts down in your work by 1/7, theoretically. but ultimately you'll probably want to rehash things at some point, right? Okay, I see no questions. So reminder, on Monday we'll go ahead and finish up with hashing, and then we'll do a review in anticipation of Tuesday, which is your midterm. The midterm will open up on midnight of Monday, so 1 second after midnight Monday. You'll have the entire 24-hour block on Tuesday to complete it and hand it in. It's open book, open note, open computer. You cannot collaborate with anybody inside or outside of the class on that, though, so keep that in mind. It will all be written. I have not written it yet, but there won't be any programming on the midterm. It's worth 100 points. That's 10% of your grade. It's due, unfortunately, on the same day as your assignment 2, so I would highly recommend that you get that done before Tuesday and give yourself enough time on Tuesday in order to get the midterm done. There's only going to be like 4 or 5 questions, so it's not going to be huge and long. It's not going to be designed for 24 hours, certainly. But we will be going over last year's midterm, maybe the midterm before, depending on how much time we have. All right. All right. Have a great weekend.